Year 1 Further Pure, Chapter 4 Matrices and Their Inverses, Lesson 1 The Determinant of a 2 by 2 Matrix. So let's consider a 2 by 2 matrix which we will call M. And M is going to be the matrix A, B, C, D, going across the rows like that. Now, we can identify the determinant of this matrix, and we call this det M, or sometimes mod M. They both mean the same thing, they mean the determinant of M. Now, to calculate the determinant, we work out A multiplied by D, subtract B multiplied by C. And that's how we calculate the determinant of a 2 by 2 matrix. The determinant is sometimes also referred to as delta. So if you see that symbol, you know that means determinant as well. Now, let's have a look at a quick example of this. So let's say M is equal to 4, 3, -2 and 5, then the determinant of M, using whichever notation you wish, would be 4 multiplied by 5, subtract 3 multiplied by -2, which comes to a value of 26. Let's look at another example. M is equal to 1, 5, 7 and 2 here. So the determinant of M is equal to 1 multiplied by 2 minus 5 multiplied by 7. So that is equal to 2 minus 35, which is equal to -33. So determinants can be positive, they can be negative, they can be equal to 0. They do not have to be integer values as well, depending on the components of your matrix. So we're going to identify a matrix M, which is 5, 1, 3, 2. And we're going to try and work out what the determinant of this matrix actually tells us. So let's calculate the determinant of this matrix. We can see that mod M, det M, is equal to 5 times 2 take away 3 times 1. So that's equal to 7. And we're now going to try and work out what happens when we apply this matrix to a set of coordinates. So have a look at the diagram, and can you see the unit square A, B, C, D? Now, what I'm going to do is I'm going to take this matrix M and I'm going to apply it to each of the coordinates, and I'm going to set the coordinates up as a matrix. So you can see point A is 0, 0, point B is 0, 1, point C, 1, 1, and point D, 1, 0. And we're going to see what happens when we apply the matrix to each of those coordinates, which we can do as a matrix multiplication. So this is equal to 5, 1, 3, 2 multiplied by 0, 0, 0, 1, 1, 1, 1, 0. So to work out the effect of the matrix on each of the coordinates, because remember, matrices represent different types of transformation, we simply have to do a matrix multiplication. Now, there are lots of ways in which people like to do matrix multiplications. I like to ring off pairs like this. So you may have to refresh your knowledge of matrix multiplication. So I start with 5 times 0 plus 1 times 0, which is 0. Then 3 times 0 plus 2 times 0, which is 0. And then I move on to B, which is this pair of coordinates here. 5 times 0 plus 1 times 1 gives me 1. 3 times 0 plus 2 times 1 gives me 2. And then I move on to the third pair here. 5 times 1 plus 1 times 1 gives me 6. 3 times 1 plus 2 times 1 gives me 5. And then for the last pair, I then have to do 5 times 1 plus 1 times 0, which is just 5. 3 times 1 plus 2 times 0 then just gives me 3. And these are the image coordinates. So this would be A dash, B dash, C dash, D dash, the image of each of the object coordinates under the transformation represented by M. And we're going to plot these. Now, A dash remains exactly where A is, so no change there. B dash is now 1, 2, so that's this point here. C dash is 6, 5, so that's over there. And D dash is 5, 3, so that's this point over here. And what I'm going to do is use a series of straight lines to join up the new coordinates on the object. And have a look, we've created a parallelogram. You can see that outlined here. Now, let's explore what the determinant, which if you remember was a value of 7, has actually worked out. So the first thing that I'm going to do is calculate the area of the unit square, A, B, C, D, and as it's a unit square by definition, its area is 1 square unit. And now we're going to work out the area of the parallelogram. Now, how do we go about doing that? Well, there are lots of ways in which we could do this. An easy way is to actually notice that we could work out the area of this rectangle overall and then subtract the areas that we don't wish to include. So if I split off here and if I split off here, then we can see we have a pair of identical trapezia and a pair of identical right-angled triangles. Can you see them? There's a right-angled triangle here and a right-angled triangle here, and then there's a trapezium here and an identical trapezium here. And if we subtract these areas from the overall area of the rectangle, we will get the area of A dash, B dash, C dash, D dash, which we will do now. So here we go. Here's the area of the parallelogram. The calculation you can see listed here, and the area works out to be equal to 7. So what does the determinant tell us? The determinant is the area scale factor of the transformation. We start with a unit square of an area of 1 and we end up with a parallelogram with an area of 7. So the determinant of the matrix tells us the area scale factor of the transformation. So just to summarise, the determinant of a matrix M is the area scale factor of the transformation represented by M. It tells you how much the area will be scaled up by if you apply that matrix, that transformation, to a shape represented by a set of coordinates. So what happens if a determinant is negative, given that we have established that the determinant represents the area scale factor of a matrix transformation? So I'm going to let M be the matrix 1, 6, 1, 2. Now if we calculate the determinant of this matrix, we can see that the determinant of M is equal to -4. And what we're going to do is we're going to apply this matrix again to the set of coordinates which represent the unit square A, B, C, D, and I'll do it in that order. So let's fill in the coordinates and using any technique you wish, perform the matrix multiplication and see whether you get the correct answer. So if you've done this correctly, you should get this matrix here. And what I'm going to do is plot the coordinates of the object. So A remained invariant, but B is now the point B dash over here. C is now this point over here, and D is this point over here. So this is interesting, and I'm now going to use a series of straight lines to join up A, B, C, and D. So as you can see, we have another parallelogram, and we're going to do exactly the same thing as before. We're going to work out the area of this parallelogram using a similar strategy to previously. So performing the calculation, like last time, you will find that you get an area of 4. So what does the negative scale factor actually do here? Well, you can see that the area has still scaled up by a factor of 4, so that part is still absolutely the same. But have a look at the order in which the coordinates feature. So previously, if we went from A to B to C to D and back to A, we were working in a clockwise sense. Whereas for our new shape, let's have a look at the direction in which we move. So if we go from A to B, then to C, back down to D, and then back to A, can you see we've traversed the coordinates in an anti-clockwise direction? If your matrix has a negative determinant, the magnitude of that determinant will still be the area scale factor, but the fact that it is negative means it changes the sense of the vertices from clockwise to anti-clockwise, anti-clockwise to clockwise, or it changes the order in which you can traverse the vertices. So we're going to explore an interesting rule. Let's test it out using an example first of all. So we're going to let m equal 1, 2, 3, 4, and we're going to let n equal 5, 1, 0, 2, and we're going to work out the matrix Mn. So do that first of all. Work out what the matrix Mn is, please. The product of M and N. And remember, order matters, so it's got to be M on the left and N on the right. Remember, matrix multiplication is not necessarily commutative, and order matters. So let's see what we get for this. So you should find that you get 7, 4, 19, and 8. Now the next thing that we're going to do is work out the determinant of M, which works out to be -2, the determinant of N, which works out to be 10, and the determinant of Mn, which works out to be -20. Now, hopefully, you should see the connection straight away here. We should see that the determinant of Mn is equal to the determinant of M multiplied by the determinant of N. Now, this should make perfect sense. Remember, we're saying that applying a matrix means performing a transformation, and if you have one transformation followed by another transformation, let's suppose the first transformation has a particular area scale factor, which multiplies up the area. The second matrix transformation will then multiply up that area as well, and so you can get the overall scale factor by multiplying the individual scale factors together. Now, can we actually prove this result algebraically? Well, let's allow M to equal the matrix A, B, C, D, and let's allow N to equal the matrix P, Q, R, S. Now, the matrix Mn is then going to be a little bit more complex, but we can work it out using matrix multiplication. Take great care with your algebra here. Can you work out the matrix Mn, please? Did you get it right? Let's see. You should have got AP plus BR here, AQ plus BS here, CP plus DR here, and CQ plus DS here. And the next thing that we're going to do is work out the determinants of each of these matrices. So det M, which, by the way, if I wanted to, I could write this as well to mean the same thing, is equal to AD minus BC. Now, similarly, det N is equal to PS minus QR. Now, let's work out the determinant of Mn, which involves slightly more complex algebra. Be very careful as you work it out. Obviously, you have to do this multiplied by this, subtract this multiplied by this. So here's the algebraic calculation you've got to do. Expand these brackets and see what you get. So, having completed the algebra, you should find you get 8 initial terms like this, But as you will discover, some of these cancel out with each other. So APCQ will cancel out with AQCP over here, and BRDS will cancel out with BSDR over here. So we're left with 4 terms. So here are our 4 terms. And what I'm now going to do is look for where I can see some common factors. Now here, these terms here both feature an A and a D. And here, these terms both feature a B and a C. So I'm going to factorise from the green parts AD, which leaves me with PS minus RQ, or QR. And then for the yellow parts, I'm going to factorise BC, leaving me with RQ minus PS. Now, notice something. These two are the same, but with a factor of -1 involved here. So I'm going to rewrite this as AD PS minus RQ, so that stays the same, but I'm going to have a negative here, take a negative out as well. So in the second bracket, this swaps around to give me PS minus RQ. Now, I can factorise out this whole linear factor here, which then gives me the result AD minus BC multiplied by PS minus RQ. Now, what do we know about these? Well, AD minus BC is equal to the determinant of M, and PS minus QR is the determinant of N from previously. So this very nicely creates a little algebraic proof of the result. So to summarise, we know that the determinant of the product of matrices Mn is equal to the determinant of M multiplied by the determinant of N, and this makes perfect sense because M and N represent transformations involving scale factors of area, and if you're applying, for example, an area scale factor of 2 followed by an area scale factor of 3, that's the same as applying a single area scale factor of 6. So if a matrix represents the area scale factor of a transformation, what does it mean if a matrix has a determinant of 0? So I'm going to let M equal 6, 4, 3, 2, and you can see for yourself straight away that in this case, the determinant of M is equal to 0. So what happens when we apply M to our unit square again? So let's do that with a matrix multiplication and see what happens. Let's check if you got this correct. These should be the coordinates of your. So let's plot these. So A again is invariant, so A dash is simply here. B dash is 4, 2, which is there. C dash is 10, 5, which is there. And D dash is 6, 3, which is here. Now, join up points A, B, C and D, the dash versions. Now, what do you find? You find that all 4 of the coordinates have been mapped to a single straight line. And what's the area of a straight line? The area of a straight line is 0, which matches the determinant. Remember, the determinant tells you the area scale factor here. Now, we can look at this in a general sense. Let's take the matrix M again, and let's apply it to a general coordinate xy, which could be any point in the Cartesian plane. It doesn't necessarily have to be a point on the unit square. The use of the unit square is just so that it makes it easier for us to see and understand the area scale factor connection with the determinant. xy could be any point in the Cartesian plane. Now, if I apply the matrix M to xy, what do I get? Well, let's do the matrix multiplication, and we find that we get 6x plus 4y here, and then 3x plus 2y here. Now, these are equal to the new x and the new y. So look at the connection. Can you see that the new y is equal to half of the new x? So all of the points in the plane are being mapped onto the line y equals a half x, and you can see that line here. So under the matrix M, every point in the Cartesian plane is mapped to a point on the line y equals 1/2 of x, and we should also note that multiple points can be mapped to the same point on this straight line. This will become important a little bit later on when we're thinking about inverse matrices. So for instance, try applying the matrix M to the coordinates 4, 0 and 0, 6, and you will find that in both cases these object points are mapped to the same image point 24, 12. So multiple points can be mapped to the same point on the image straight line. And as I said, this will be very, very important when we're thinking about inverse matrices and what happens when a matrix has a determinant of 0, because this will be a special case we have to think about very carefully.